Yeah, so I'll just write out what I said in more compact terms. For any n, there exists an xn inside the set A that we are looking at, such that sup
Xn
A,
converge.
yeah,
Does Xn converge to?
yes, basically that's where we are getting at. So what
Yeah.
I'm basically trying to say is that I'm trying to build it from supremum and then saying that this is bringing us to sequences. Okay,
Yeah.
and we will define convergence from here. But let's see. So this is what we are getting, right? That the supremum is arbitrarily close to the set. If you take a degree of closeness that is 1 by n, then you'll find an xn, which is, that much 1 by n degree close to sup A. Okay, so that's what we have for the supremum. Right. Now, this is clear for everyone. So, in fact, what have we been able to do? We have replaced that for any epsilon greater than 0, which is an uncountable statement, to a countable statement, right? For any n in naturals. That's definitely an upshot. Okay. So basically you have, I mean, roughly speaking, you have this sequence x1, x2, x3, which is becoming arbitrarily close to sup A. You mention a degree of closeness, I will give you an xn. So when I say you mention a degree of closeness, you can mention any degree of closeness. Okay, you can mention any epsilon. You give me any epsilon. The good thing is that I can find n such that 1 by n is less than epsilon. And hence I can take my xn and that xn will do the job.
Archimedean property.
Yes, exactly. Very good. Yeah. Such that this will be less than, I'm sorry, this will be less than epsilon. So here we are using the Archimedean property of the natural numbers, or which is the same as Q is dense in R. Think about it, right? We are saying that for any epsilon,
Archimedean property of natural numbers.
it is the Archimedean property of natural numbers. When you can state it like that, right? So this is n epsilon greater than 0. For any epsilon, you have a n such that n epsilon is greater than 1. Right. That is called the Archimedean property, but I have not introduced that. So I will say it from a different perspective. Okay. But this is something which is very clear, so all of us know it. But let me just build it from the way I have been building it. Now, what my perspective of it is that this is essentially saying that taking any epsilon, you can get a n such that 1 by n is less than that. Right? This is a property of rational numbers, and this is basically the denseness property of the rational numbers, right? Because if it happens around 0, then you can use the arithmetic, shift it, and make it happen everywhere on the real line. Okay, so here we are using the fact that from my perspective, the way I see it is Q is dense in R. This is basically Q is dense in R. Now you can call it the Archimedean property. You can show that from there, you can prove this, from here you can prove that. We can show both ways. Anyways, point is this. So the all of this is working. We are able to have a countable parameterization of an uncountable set, which is R. Because the way we constructed the R, we were very careful. We only added the important things and we made Q dense in R. That's why it's happening. So in later on in mathematics, you will see that when you are defining a dense set and when you're completing it, you make sure that the completion the initial set was dense, so you don't add extra elements. And so even though the new bigger thing helps you to do all the analysis, but still a lot of statements can be written by using the smaller set which you started with. Okay, so that's what's really happening, a countable parameterization of the supremum property. But I mean, this will not be useful unless this implies some, I mean, it will not be useful unless this is equivalent to the supremum property. So what I mean is, you take a set, I mean, you take A and you take a number L. Okay. If the same thing happens for L, I mean, of course, L has to be an upper bound to start with. Otherwise, this doesn't make much sense. So L is an upper bound to start with, right? L is upper bound. Now, if L is such an upper bound that for any epsilon or for any n you take, okay, there will be an extent that L minus xn is that much close to is less than 1 by n, then it also implies that L is a supremum, right? So this is also quite clear, right? Because if you take anything less than that, if you take anything less than L, right, you take an L minus epsilon, then you can find something. That's what this property is saying. So which means that L is the least upper bound. So this is equivalent to the supremum. Okay, so we have a new definition of the supremum basically. Okay, so so an upper bound is the supremum if there is a sequence that basically converges to it. This is the definition of convergence, you could say. Okay, basically there's a sequence which becomes close to it and remains close to it. Means the later terms, obviously the later terms would also have the same property, right? Yeah, so this will help us in problem solving. It will help us to find supremums, because these sequences are what we can list and what we are used to working with and can work with. Okay, so when we are asked to find supremums of a set of which is defined into of a set, then we take all kinds of all kinds of candidate sequences and see which one has the biggest limit, right? Which is the biggest place where all these sequences can go, and we declare that as the supremum. Okay, so for example, let's take a simple example, and in the problems we can do a harder example later on. So yeah, let's start. Let's take the example. So what example can I take? Maybe we can take something like, yeah, how about this? M by M plus N, where M and N are in naturals. Yeah, so this is a set, okay, A. So the question is, find the sup of A, and we could also find the inf of A, both these things. So yeah, please try it. Yeah. Okay. Any guesses also what the supremum should be?
I think infimum will be 0 and supremum.
So infimum, he's saying it's 0.
Yeah, it's 0.
Okay. And so basically think about how big can you make it. You have the freedom of choosing M and N, and try to think how big
half,
you
I
can.
think, half.
Half.
Half. This M and N is completely free. It's completely up to you. Oh, let me think. Is it half? No, I don't think it is half. How big can you make it? What if so already half is not
or
a good
3 by 4. Half or 3 by 4.
3 by 4. Okay, what if I take 100 by 101? This is there, right? If M is 1 and N is 100. Sorry, I mean, M is 100 and N is 1. I can make it 100 by 101.
Supremum can be 1, right?
Yes, right. Supremum is 1, right? Because
Yeah.
as you can see, you can take it as close to 1 as you want.
Yeah.
Right? Yeah. So clearly, now how do you prove these things? You can prove it by the core definition also. No problem with that. But let me just show you a proof. Yeah, please.
We can create a sequence. I think.
Yes, exactly. That's the thing. So, but before that, make sure that you show that it's an upper bound. You have to show that one is an upper bound. So one is an upper bound has to be checked. Okay, which is of course trivially checked, but I'm just saying, okay, upper bound, and then you can create a sequence that tends to it. That you all can do it. Just take the sequence itself, over M, and you can show that it's going towards that. So very good, right? Very easy, right? Yes, so that's what it is. Some easy questions. So now let's move on. Right? So if you look at the supremum and you look at the better definition of the supremum that we got, then really the very important point was that Q is dense in R, right? Is dense in R. This helped us to give a good definition of Q, of the supremum of a set, a good sequential definition. And this is kind of also telling us that a lot of properties of sets and subsets can be better understood, or can be more easily understood and equally powerfully understood if we just study sequences. So this motivates us to do two things: to study sequences better in a closer angle. Okay, instead of sets, study sequences instead of sets. That's what it's telling us. Instead of sets. And number two, study dense sets. Try to figure out which other sets are dense, because already this is helping you. Study dense sets is the other thing. So let's just study dense sets first, okay? Then we can go into sequences as well. So dense sets. So I'll just start with dense sets of R. I will not go in too much generality. So before doing anything, let's define it very clearly, okay? So let me put the context. A subset of R. A is dense in R if, or the definition is. So yeah, can anyone please define it?
Yeah, A is dense. Can I define it
Yes.
in terms of limit point? Limit point.
No, not in terms of limit points. Define it without that.
Oh, then A is dense in R if we have a every point in R is basically a supremum of some subset of A.
That's good. Noel, are you saying something?
No.
Oh no, someone was saying hello. Who's saying hello? No, sorry, probably it's my mistake. Yeah. So he has quickly adjusted to what I asked, and he has given a very good definition. In fact, he just used the supremum. Okay, so he's saying that if so probably write it like this: every element of R is the supremum of something. I'll just say something in A, some subset of A. I mean, some subset of A, right? So yeah, Noel, can you give us a different perspective, or can you expand on this? Just want to see your understanding of this. Or Anish, you're also here. You could try to explain it further. Okay. So
we can also
yeah.
say, can we say open sets? Open sets means open intervals.
Open intervals. Yeah, you can say it in terms of open intervals. Okay. Try to. Let's see.
Basically, it intersects with every open sets. Open intervals.
That's right. That's right. But yeah, that is just another definition. I mean, that's the way you're saying it sounds very disconnected. It is connected, but maybe it's obvious to you. It's obvious to me also, maybe. But yeah, we have to make it obvious too. Okay, let's see. So let me first give the intuition about dense sets are. Okay, so well, dense if something is dense in something, it means that, this is like everywhere, right? So when we say that an element is dense, what do we mean? We mean that it's molecule. So if there is a space which that element occupies, then whatever fundamental particles we are considering, it's everywhere in that, right? Whatever tiny piece of space, you take, there is something of that matter which is there in that space. For example, iron is dense, so it's the atoms are almost everywhere present in any piece of space you take. Okay, so here the space would be an open interval. Okay, so given any open interval in R, or I can say in other words, open interval x comma y in R, there exists a Z, or maybe I can just say there exists an A in A. There exists one atom of that element, iron or whatever. Okay.
Sir,
Yeah.
does the definition of just I'm saying one thing is the definition of limit defining the subset is dense in some set. Limit point is, I think, more fundamental because the way you said that it is everywhere in that set.
Yes, that is right. But I have not yet got to limit points. Okay. Limit points are very fundamental. I agree. They are in fact more fundamental than limits. I believe. Yeah, right. I agree with you. Yes, even more fundamental than supremum. So maybe I might have approached it like that, but that approach would be quite complicated. So limit points are basically, something like for other people also. We will define it, but see, the problem is I want to go with the approach that I've taken. But yeah, I agree with you. So basically, we have a set. It may not have a uniform structure. Okay, so it's like in a lot of places, somewhere it's more, somewhere it's less. Okay, then the thing is that there may be like these pieces may have a supremum here somewhere. So this subset may have a supremum here. This may have a supremum here. So it's like kind of a lot of supremums are there, right, for the various subsets. Okay, which maybe not in the set. So those pieces are like the sinks of those rivers. Okay, whatever, something like that, of those drain systems, whatever. Okay, so those are like the places where a lot of terms in the sequence accumulate. Okay, so these are basically what limit points are, but we will define them more clearly. But the way that's these are actually more fundamental because these come first, and we want these things to have in our set so that our set has this, it because when you're taking a process, usually the result happens when you take infinitely many iterations. So the answer really lies in the limit point, not usually in the set. If it's in the set, it's good. So we would want to have these things in our set, and these things, as you can see, are supremums of something or the other. Okay, so I should have taken this first and then taken out supremum from there and then gone through the subject. But it would be a slightly complicated thing to do in the beginning. That's why I started with supremums. Okay, but we will come to limit points, and that's actually very fundamental, as he said. Yeah, not the most, but it's not the most simplest. That's the problem. Okay, but anyways, let's take this approach. So x comma y is there. There exists an A such that x is less than A is less than y. As simple as that. Okay, so this is our definition of denseness. Okay, and yeah, and what he's saying here, one so what he's saying here is also equivalent, right? Because it is a supremum of something, right? So what you can do is you can take an x and you can take x plus 1, you'll find an A, right? Every element of R is a supremum of something. So I am going to show the infimum, so probably I should do the other way. But you can understand, right? You can get things arbitrarily close to it. So you can probably just take a y and take a y minus 1 by n, you get an A. And then you y minus 1, then you take a y minus 1 by 100, you get a B. And you keep getting things, and A and B are all in A, and you keep getting things like this which go closer and closer to B, but all less, or go closer and closer to Y, but all less than Y. And so the supremum of those things will be Y. So that's an equivalent thing. That's why supremums are so fundamental. Okay, but again, we can also state this, but also we can state this in terms of sequences as well, because supremums can be stated in terms of sequences. But before going into all those equivalent definitions and all, which are probably something that can just work out also, I would want to just see some other dense sets of R. Okay, so that we can actually work with these things and find these things. Okay, before we say more. Yeah. So really, the other question that I have is that there are other problems which I will give some interesting dense sets. But before that, I would just want you people to show that Q complement. This is the definition of irrational numbers. Q complement. Q complement is dense in R. So this doesn't always happen. When you complete a set, maybe it doesn't always happen that this complement set is also like you have a set and you complete it, you make it have the supremum property and you get a bigger set, which in this case is R and previous is Q. We are showing that in fact this thing is also dense in R, which means my picture is horribly incorrect because should be everywhere, right? But you understand my point, yeah? So, but in this case, this happens. Q complement is also dense in R. So yeah, people try to prove this now. And
Basically, due to dense property, density theorem, I think.
okay, which theorem are we going to use?
Density property of irrationals.
But
But that's what I'm asking you to
irrationals we
prove.
haven't defined, right?
So irrationals by definition is Q complement, right? But when Subham
Hmm.
is saying density property of irrationals, that's what I'm asking you
Yeah,
to prove.
that is what is to
Is
be
the
proved.
question? Yeah. So that's what the question is.
What I could not get.
Um, so I'm just saying that like the collection of numbers which are not rational, they are dense in R.
Oh,
So
I need to prove this now.
yes, 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 yeah. This is the claim.
Oh, acha, acha. Yeah, yeah. This
And
is
yes. No, but yeah, they were right. So Anish is saying by the density of Q, there exists an R in X comma Y. But we want to show that there exists a R in Q complement that is in X comma Y. Okay, Anish. So I hope you are understanding my point. And if you expand on it, maybe your point will prove it, but you have to state say more. But if you just say like this, and you just say that there is an R in Q, that doesn't say anything. We want something in Q complement which is here. And you can't say that the size of Q complement is uncountable and hence it is true. No. And size, that cardinality has not much to do with this denseness thing. Both are notions of bigness, how big this is comparatively, but this has to be to do with the distribution also. Yes, Anish, but what is the R? The R is in X comma Y and the R is rational. We want an irrational that will do it.
so if we consider two real numbers,
Okay,
say
just give me
x
one
and y.
second. Just sorry, 1 second. He's saying something else. So since y minus r by 2 by Archimedean property, there exists the n in n such that. But again, where is the irrational, Anish? I'm not seeing that. Where is the irrational number? I don't know. So yeah, Subham, you're saying something.
If we consider we know the denseness of rational in R. So if we
Hmm.
consider two real numbers, say x and y, we need to
Hmm.
find an irrational such that which lies in open interval x comma y. Now
Yes.
root. So if we consider root 3x and root 3y are also real numbers. So by density property of rationals, we know that there exists a rational number in root 3x and root 3y. So
Hmm.
uh, so if you just take that, let it be p. So p by root 3 is basically in x and y. So p by root 3 is irrational.
Yes. Right. Which
So
is
in this
right.
way,
I think now Anish was also saying something similar late. Yeah. Square root. Yeah, but you should have said this before. Yeah. Yes, yes, Anish. Now your point is making sense to me. Yeah, so you should have said this earlier. Right. So basically, we are saying that these irrational numbers, but here we are very strongly using the arithmetic, right? That irrational and rationals have this very good arithmetic that when you multiply them, multiply a rational and irrational, it becomes irrational. If you think about it, this is not easy to prove. Multiplying a rational with an irrational is irrational is not very easy to prove if you use the definition of irrationals that we have used. Like you have to then use the fact that this x is the
P by Q.
no, not the p by q. That is a no. See, root 3x. Okay, probably. Hmm.
P by Q, I think
Yeah,
will
you can
work.
use that definition. Yes, yeah, it just works out. Yeah, so yeah, it's easy to prove. So I was thinking that no. I'm sorry, you're right. Yeah, you're right. I was just overcomplicating the thing. Yes, but at the end of the day, we have this very good arithmetic, right? That we can multiply and so on, right? So that really makes it work out. It doesn't happen always. I feel it doesn't always happen when you complete a set. I'm not sure if the complement is always dense here because here we are using the arithmetic, and I don't know a proof that does not use the arithmetic. Okay. So yeah, I mean, yeah, that is the thing. Okay, so this is a good example of a dense set. Okay, um, there will be other examples that we will be doing soon. Yeah, so that I'll give in the problem sets first, and then we'll discuss it a little better. Here we can do more theory in the class. So where do we go from here? Now we should study sequences, right? We should study
And there is a
sequences.
very
Mm-hmm. Yeah, please say.
if we have money in context of denseness, I think there is a very good problem which shows that a subset, say A of R, is dense or not. Why? And we need little bit of group theory, I think, in that every
Yes.
subset
Yeah, that's a very interesting.
is
I
either dense or cyclic. And that
Yeah,
will.
yeah. Right. So that we will discuss. Basically, I was going to give that in the problem set, and we can discuss the idea of that because the core idea of that is very interesting. Yeah. So I'll want everyone to try it first, then we'll discuss it. Okay. So I think we will just stop here, right? Because we started at 10:25. So we can just, because the next thing I want to do. So let me just give you the plan for the next class. So of course, I'll give you lots of problems, and you can also try problems from different places and challenge me. Okay. It will be good for me also, right? But apart from that, we will study maybe more techniques to show denseness. We will see if we need to more techniques for denseness, maybe. That's number one. And number two, as we are understanding, the supremums are very important. Sorry, I mean, supremums can be studied by sequences. So we'll study sequences, right? Sequences and their limits, okay? Limits or limit points. Okay, we'll study these. Then we will see which sequences clearly have limit points. We will have monotonic sequences, and then we will see how well we can find them. Okay, and we will try to separate the combinatorics from the analysis there. Yeah, then we will have a lot of limit points, a lot of good ways to finding limit points, and yeah, that will be probably the content of the next class because we'll have some proving to do there. And yeah, then we can go into Cauchy sequences mostly. Okay, and we'll see how they are very interesting because they really remove the limit from the thing. We don't have to really find the limit, or yeah, we'll see that. Yeah. Okay. Yes, so that's it for the day. All right, so then next class I will announce, probably mostly it will be next week. Okay, but I will consult everyone and see what we should do. Okay, so I hope it's okay for everyone. And then okay, then see you next week. Anish, you came a bit late today. Yeah, but try to come on time, but never mind. Yeah, I hope everything is clear. Okay, then see you.